Hello, welcome to the solution manual for assignment 6. Jumping right in, let's get started with number 1. Add or subtract the following vectors to find the resultant vector. Okay, so 1a, 5 meters north plus 7 meters west. Quick little diagram. I have 5 meters north, 7 meters west. Remember, we connect them tip to tail, so it's kind of like I've just drawn 7 meters west and then 5 meters north. Perfectly fine. Our resultant vector will be, draw it in green, right there. So I'll call that R. 5 meters north, 7 meters west. So we are looking to find that resultant vector. To do this, we see that we have a right angle triangle. We know 2 of the side lengths. We can use Pythagorean theorem here. So we see that R is equal to the square root of 5 squared plus 7 squared, which is going to give you about 8.6. And because we're given 5 and 7 here on a right angle triangle, I'm going to use tangent. And I know that the tangent of this angle here, angle theta, I know that the angle theta can be written as theta equals the inverse tangent of 5 over 7. Now, careful, a lot of people got this part mixed up. 5 over 7 with the directions. The directions in general for a lot of these questions were mixed up. In SOHCAHTOA, tangent is with opposite over adjacent. In this case, my angle theta, the opposite side of that is 5. So the 5 goes over the 7. Punching this calculator, you get about 36 degrees. So my final answer becomes R equals 8.6 meters west, 36 degrees north. Again, this last part here where you write out the direction, people got this part confused quite a bit, the part I just circled right there. A lot of people would write north 36 degrees west instead by accident. The reason I've written it as west 36 degrees north, very important. Here on our chart, our vector triangle, this is the measure. This angle theta is measured from the horizontal going to the left here, which is west, and it's measured upwards. So we're starting at west, we go up 36 degrees towards north. And that is how I come up with the direction here. I'm going to quickly shrink this down a little, or not. Apparently all of this wants to move as one. Never mind then. Okay. Part B. This one was either a longer calculation or a shorter one, depending on if you saw the shortcut that you could take. And I'm just going to divide this page up nicely for myself here. So, part B, there was a bit of a shortcut. Let's see what it is. First, I'm going to draw a short little graph of this. I'm going to draw this first one here in green, and I'll draw this one over here in blue later. So green one first. I have 11 over 15, so a little bit less than 1 kilometers east, 30 degrees south. So if this branch on the right here is east, I'm going to start here, and I'm going to go 30 degrees south, and I know my vector is in that direction. I know that is 30 degrees. The other one, 5 kilometers west, 30 degrees north. So I'm going to start here on the left, that's west, and I'm going to go 30 degrees up. Now, these are being subtracted. So, subtraction is the same as writing adding negative 5 kilometers west, 30 degrees north. It's the same as writing that. And this negative here, I can swap the directions 180 degrees. So if I were to go 1 kilometer north, that's the same as going negative 1 kilometer south. Using the exact same logic here, we can flip that and have it say plus 5 kilometers. Now, opposite of west is east. Keep the number the same. Opposite of north is south. And all of a sudden, we have plus 5 kilometers east, 30 degrees south. And if I were to draw that in here, it would be the exact same vector as the green one, just a different length. This one's much, much larger. I have not drawn them to scale, but they go in the exact same direction. So we don't need to actually break these into components at all. And we can directly add, directly add 11 over 15 plus 5 equals about 5.73 repeated. And then we get a resultant vector of 5.73 kilometers east, 30 degrees south. And that is our final answer with the shortcut. Now, what if you did not see the shortcut? Well, you can break all of these up into components. I'm going to call one of these vector A, one of these vector B. Sure. I'll call one blue, one blue, one green. Let's do that instead, not A and B. One blue, one green. So for the blue one here, this is 5 kilometers west, 30 degrees north. So I know the length there is 5. For the green one, I know that it is 11 over 15. Now, for the blue vector, our x component, just call it x in blue, so blue x, is going to be 5 times the cosine of 30, which is about 4.3. And this is kilometers west. Very similarly for y, we got sine 30. This gives us 2.5 kilometers north. And for green, we do basically the exact same thing to find the x and y. We get 11 over 15 times the cosine of 30 times the sine of 30, exactly how we just did it. And here we are going to get 0.6 kilometers east and 0.37 kilometers south. Okay, so now we are looking for our resultant. So the x component of the resultant and the y component of the resultant. Here, for the x component of the resultant, we are going to have the x component of the green one minus the x component of the blue one. Remember, we are subtracting these two vectors. If we get very beginning of this problem here, we had green subtracting blue. So that is why we are subtracting them in this order specifically. And that will give us 0.6 minus, now, this is 0.6 east. I'm currently trying to subtract 4.3 kilometers west. I need these both to be in the same direction, so I'll flip west to east, and that will give me negative 4.3 east. Now these are both east, and adding these together, because these two subtractions multiply to create a positive, I'm going to get 4.9. And overall, that is east. There we go, east. All right, same thing with y. So green y minus blue y. Green y, we get 0.37. That is south. For blue, we have 2.5 north, so I'm going to sub that in for negative 2.5 south. And that gives us 2.87 south. Our total resultant vector is just going to be using the Pythagorean theorem, so 4.9 squared plus 2.87 squared equals 5 point, I'm getting 6.8 kilometers here. And to find the angle, we can take the tangent between the x and y components here. So theta equals the inverse tangent of opposite over adjacent. The opposite in this case is going to be our y. So we're going to have 2.87 over 4.9, and theta, this is going to be very, very, very close to 30 degrees, close enough that I'm going to round it to 30 degrees. And then putting these two together, the magnitude and the direction, we get a resultant vector of 5.68 kilometers. Now this is east, 30 degrees south. Again, I know I'm going east and 30 degrees south because if I were to draw these two vectors, it would be x component, y component. The resultant here, my angle is in between. I'm starting at the east arrow, moving south. So I know it's east 30 degrees south. The slight difference in my answers here of 5.73 and 5.68 likely comes from all the rounding I did in this longer solution method here. It took much more rounding, took much longer than the shortcut, but they both still work. No matter which way you did it, a couple of people did it, well, a bunch of people did it both ways. I gave it you the marks no matter which way you took. So, the reason why that one was only worth 2 is because there was a shortcut to take. C. From a graph, here we have a red vector that goes down 3 units, 3 squares, so 3 meters, and a green one that goes to the right 4 meters. Redrawing this so that they are being added tip to tail gives us a resultant vector here. Now, if you remember your special triangles, you will know that a 3 and a 4 on your straight sides of a right angle triangle always gives you a hypotenuse of 5. But if you didn't, you can always do the Pythagorean theorem of 3 squared plus 4 squared, and that will give you 5 anyway. So we know the magnitude is 5. Again, you could use any of the primary trigonometric ratios to figure out the angle. When I am given the x and y components and not the hypotenuse, I like to use tangent. So I'm going to go ahead and keep using tangent. So theta equals the inverse tangent of, again, this is the opposite over the adjacent. So this is 3 over 4. So our inverse tangent of 3 over 4, theta equals about 37 degrees. I'm going to round that up. So my resultant vector is 5 meters east, 37 degrees south. Again, if we were to draw these out, tip to tail, the resultant, that angle is measured from this east line downwards to the resultant. So we started east, go towards the south. So east, 37 degrees south. Lastly, part D, I give you some grosser looking magnitudes here. But if you break these down, it's really not too bad. You can see that the red one is clearly 1 unit in the x direction and 3 units in the y direction. And the green one is 2 in the x, 2 in the y. So we know that this, if we draw them tip to tail. So I'm going to draw the red one first, and then the green one. And they look something like this. And I'm going to have a resultant going like that. I know that I can break these up into 2 separate triangles, a green one and a red one. I know that the green x is going to be equal to 2 units, and the green y is equal to 2 units. I know that the red x is equal to 1, and the red y is equal to 3. And these are the components. You can go ahead and double check if you would like. You can see that the hypotenuse in red is equal to the square root of 1 squared plus 3 squared, which is equal to square root of 10. And for green, you can do the same. Square root of 2 squared plus 2 squared. That will simplify down to 4 plus 4, which is 8. Square root of 8, which is equal to 4 times 2, which is equal to the square root of 4 times the square root of 2. And the square root of 4 is just 2 times the square root of 2. So they do in fact work out, in case you wanted to prove it to yourself. But back to the resultant. The resultant, of course, is just going to be the components of the 2 other vectors added together. So I'm going to have, for Rx, I'm going to have the red x plus the green x, which is going to be 1 plus 2. So Rx equals 3. Ry is going to be the same here, but with the y components. So Ry equals 3 plus 2, which gives us 5. So 3 and 5 are our components here. Now, the 5 is not the hypotenuse. 5 is not the hypotenuse. The 5 is our y value here, and 3 is the x value. That means that we cannot use the special triangle. This is not a 3, 4, 5 triangle. This is a 3, 5, whatever the hypotenuse ends up being triangle. So we cannot do the same quick little shortcut that was an option in part C. So Pythagorean theorem it is. So we have r equals square root of 3 squared plus 5 squared. And our resultant is about 5.8. Again, like normal, theta equals the inverse tangent, the opposite over the adjacent. We're looking at this angle inside here. Opposite is 5, adjacent is 3. Theta equals, I get 59 degrees here. 59 degrees. So my final resultant vector is 5.8 meters. And this is east. We are going towards north. We're going up. So this is east, 59 degrees north. I guess I should circle this answer over here for part C too. But that was question 1. All parts completed. Number 2 here. Find the resultant vector. So I'm going to start by drawing a little diagram here. I'm going to put this one in red, this one in green, this one in blue. So first I'm going to have 7 kilometers west. Then I have 2.025 kilometers south. And I'm kind of drawing these to scale, not perfectly. And now I have negative 18 kilometers north, 45 degrees east, which would look like this for 18 kilometers north, 45 degrees east, but this is negative, so we have to flip the direction. So it's actually going to look like this. It's actually going to look different. And our resultant is there. So I am going to label these vectors A, B, and C, just to keep track of them. And I see right off the bat that vector C is the only one that I actually really have to break into components here. So I'm going to have Cx and Cy. And when I break everything into components, I see that the x value for Rx is just going to be composed of a vector A plus Cx, and Ry is going to be vector B plus Cy. So let's get calculating what Cx and Cy are. So Cx is going to be equal to 18 cos 45. And that's going to give us 12.7. Now, because this is a 45-degree angle, our calculation is actually going to be the exact same. So we're going to get 12.7 for both here. Now, this is negative 18 kilometers north, 45 degrees east. That negative flips the directions. So this is actually going to be plus 18 kilometers south, 45 degrees west. So the x component here is actually west. The y component is actually south. And that matches up with the directions for vectors A and B perfectly. So when we go and sub in, we don't have to worry about directions anymore. So subbing in, A, we got 7 kilometers plus 12.7 for our x, and that gives us 19.7 kilometers west. Vector B is 2.025 plus 12.7 And that means our y is going to be equal to 14.725 kilometers south. And these are our x and y components of our resultant. So Pythagorean theorem, 19.7 squared plus 14.725 squared. Resultant is, I got 24.6 kilometers. Again, I'm going to use tangent. Theta equals, for the direction, tangent, our opposite is the 14.725 over 19.7. Theta equals about 37 degrees. So my final resultant vector is 24.6 kilometers west, 37 degrees south. Again, this here in our triangle is the angle we're looking at. Start from west, moving downwards towards south. Number 3. Find the velocity of a plane relative to the ground for a plane flying with an airspeed of 500 kilometers per hour, east 30 degrees north, and the wind speed relative to the ground is 175 kilometers per hour south. So, first what I'm going to do is write down what I know. I know that the velocity of the plane relative to the air is equal to 500 kilometers per hour east 30 degrees north. Second, I know that the velocity of the air relative to the ground is equal to 175 kilometers per hour south. And what I'm looking for is the velocity of the plane relative to the ground, VPG. So, building our relative velocity equation here. I know I want VPG. And to build that, I can do VPA plus VAG. Now, if I've set this up correctly, I will notice that I have P and a G over here, and I have a P and a G on the outside over here. The inside letter gets canceled out. So I know I've set this up correctly. So I can go ahead and plug some numbers in after I break stuff into components. I almost forgot to do that. So what our little diagram is going to look like is we're going to have about 500 kilometers per hour east 30 degrees north. We're going to have about 175 kilometers south, and then our resultant vector is VPG, and I'm looking for this angle here. I know that this angle here is 30 degrees. So I know whatever my angle is, it has to be less than 30 degrees. I also know, just from drawing this, that my angle is going to be something east, some amount of degrees north. And I know that this is going to be less than 30 degrees. So, question mark degrees is less than 30 degrees. So let's break 500 into components here. So we are going to have some ugly looking subscripts, but that is okay. Don't have to deal with them for long. VPAX and is going to be 500 times the cosine of 30, which is going to give us about 433. That should say kilometers per hour east. I'll use the units. Kilometers per hour east. VPAY is equal to 500 sine 30. That's 250 kilometers per hour north. And now we can go add these all together. So to add our velocity of the plane relative to the air, the red vectors here, with the green vector, we need them to be broken into components, what we just did. So I'm going to add the components to VAG. So I'm actually going to have VPAX plus VPAY plus VAG. Now VAG only has a Y component, so we don't really need to worry about putting subscripts, but if you want, you could totally put a Y subscript on that just to remind yourself. And in here, we have 433 kilometers per hour east plus 250 kilometers per hour north. Now, VAG is 175 kilometers per hour south. I'm going to flip that to negative 175 kilometers per hour north. I can add those two north directions together. I get 433, not 4, kilometers per hour east plus 75 kilometers per hour north. So this is the velocity of the plane relative to the ground. However, it is written in component form, and we need to correct this by using the Pythagorean theorem to get to our final velocity here, our final answer. So I know that the x component is 433, the y component is 75. So I know that VPG is equal to the square root 433 squared plus 75 squared, which gives me 439, I believe. Yeah, 439. And that means that, oh, and I need my angle now too. So that was 439 kilometers per hour. Angle, I'm going to use trusty theta again, or tangent to find theta. And here I'm going to have 75 over 433. This theta is going to give me something very, very close, just under 10 degrees. I'm going to round that up to 10 degrees. And my final answer for the velocity of the plane relative to the ground is equal to 439 kilometers per hour east, 10 degrees north. And this 10 degrees is less than the 30 that we expected it to be. So sanity check is complete. So that's questions 2 and 3. Question 4. A soccer player kicks the ball with a velocity of 22 meters per second at 35 degrees above the horizontal. The ball lands at the same height it was kicked from. That is important. That lets us use our special case equations here. So maximum height, that is our y max equation here, where we have initial velocity squared times sine squared theta I over 2g. Summing in our numbers, we have an initial velocity of 22. With these equations, you do not have to break things into components, which is very nice. The angle was 35 degrees over 2 times 9.8. That's just gravity. In this case, we are not saying that gravity is negative. Acceleration due to gravity is equal to negative 9.8 meters per second squared upwards. But, well, I'll just get rid of the direction, is equal to negative. But G is equal to 9.8 meters per second squared. Also, we know that the maximum height is going to be positive anyway, so that's sufficient in this case. Punching these in a calculator, you get about 8.1 meters. All right, and when punching these numbers into the calculator, please be careful that when you punch numbers in, you do sine bracket angle, then the squared. If you just say sine 35 squared, it will assume the angle is squared. There's a big difference here. So use the brackets. Very easy mistake to make. Find the total flight time of the ball. So we're going to use our time equation. 2vi sine theta I over g. We get 2 times 22 times the sine of 35 equals 9.8. And plugging that in gives us 2.6 seconds. Lastly, total range. That is this equation now, where we have vi squared sine 2 theta all over g. So that's 22 squared sine 2 times 35 in there over 9.8. And plugging that in, I get 46.4 meters. Range and maximum height were not vector quantities. You did not have to include a direction. So that was question 4. It was weighted a little bit more heavily as a bit of a mark boosting question. Realistically, each of these parts probably should not have been worth 3 marks, but it was there as a bit of a mark boosting question. Number 5, last question. A stunt driver launches a motorcycle off a ramp that is 2 meters above the ground, angled 25 degrees above the horizontal, with a speed of 20 meters per second. A raised landing platform is located 35 meters, horizontally from the ramp, and the top of the platform is 1 meter above the ground. Will the motorcycle land before it hits the platform, hit the side of the platform, or land on the platform? I guess there's a fourth option of completely clearing the platform, but I don't tell you how long the platform is. In this case, I guess you just assume it's an infinitely long platform. But hint, hint, it's not that. That is not what happens here. So, first thing we're going to want to do is break that initial velocity down into components. So, I'm going to take VIX, and that's just going to be VI cos theta, which is equal to 20 cosine 25, which is equal to about 18 meters per second. VIX. VIY is equal to VI sine theta 20 sine 25. Let's call this about 8.5 meters per second. And I'm going to say this is upwards. This one over here is to the right. So I'm going to say it's moving to the right and upwards. It's going off a ramp, so it kind of has to go up. Those are the directions I'm choosing. This is important because I'm choosing up to be positive. I'm choosing right to be positive. This is important later on. In projectile motion, we cannot, well, first off, we can't just use these simplified equations here, these ones, because we do not land at the same height that we launch from. So those equations do not apply. But what we do know about projectile motion is that the x and y components are independent. So when the motorcycle is in the air, the only force acting on it is gravity. We're ignoring air resistance. So the only force acting on it is gravity, which acts in the y direction. So there's no force acting on it in the horizontal, the x direction, which means that the velocity will be constant there. So I can use a constant velocity equation to figure out how long it takes to move 35 meters. So if I take my constant velocity equation, or constant acceleration equation for velocity, which is just speed equals distance over time, rearrange it for time equals distance over speed, and this will give us the time it takes to travel 35 meters moving at 18 meters per second horizontally. Again, this is a constant velocity throughout the entire motion. And this gives us about 1.94 seconds. We're going to be able to use that later. So we know it takes 1.94 seconds for the motorcycle to leave the ramp and get to leave the ramp and get to the platform. So it takes 1.94 seconds. We're going to need that later. Now, we need to figure out how high vertically that motorcycle is after 1.94 seconds. So I'm looking for delta dy. I know a couple of equations. If we look over here, we know a few of these. I'm going to use the one with initial velocity. Because I have my initial velocity in the y direction, I already calculated it. It's in green up there. I know time. I just calculated that. I know my acceleration in the y direction. That's just acceleration due to gravity. And I still know time. So we have everything we need. So our initial velocity here is 8.5. This is positive, because I've defined upwards being positive. 1.94 plus 1/2 times negative 9.8. This acceleration is downwards, so that is negative. And 1.94 squared. Punching this into the calculator, you get negative 1.95 meters. And you might be tempted to say, oh, okay, well, it obviously can't be below the ground, or below the platform, unless it crashed through or made a crater into the earth. This answer right now is telling us that the motorcycle would land before it meets the platform. However, there's one thing we have not considered. This motorcycle launches off a ramp that is 2 meters tall above the ground. So we're not starting at a height of 0 meters. That's what we've assumed so far. So we actually need to add 2 meters for the height of the launch ramp. And this will give us our true height at that point, which is about 5 centimeters. This 5 centimeters. So 5 centimeters is between 0 and 1 meter, which is the height of the ramp. So therefore, the motorcycle hits the side of the platform. And that was it for assignment 6. Thank you for listening and watching. If anyone does, I don't know. I don't check the views. Thank you for watching. If you have questions, ask.